Well, good morning, students. This is Professor Harush Patil. In the previous class, we have discussed regarding engineering seismology and structural dynamics. And structural dynamics, we have left the topic of response spectrum. In this video, I'm going to deal with only response spectrum. Let us know what is response spectrum. Response spectrum is a standard method of representation of a response of a structure to the ground acceleration. Means it is a graphical representation. You can say it is a simple graphical representation. Here, what for a ground acceleration, how the structure is going to respond, that you are making into the graphical representation. That graph or that spectrum, we'll call it as a response spectrum of the structure to the that particular ground acceleration. This is regarding response spectrum. Definition of a response spectrum you can call it is the summarization of response histories in terms of the response of all single degree of freedom systems with a different natural periods. This is the central concept in earthquake engineering. It is also a plot of maximum response of linear single degree oscillator for a given component of earthquake ground motion. So on x-axis we have natural period and on y-axis we have response quantity. On x-axis we have natural period and on y-axis we have response quantity. So this response quantity can be maximum displacement, maximum velocity and maximum acceleration. And so this response quantity can be maximum displacement, maximum velocity and maximum acceleration. So you can plot a response spectrum for displacement, for velocity, for acceleration. You can plot the response spectrum for displacement, for velocity and for acceleration. Now we'll discuss the concept of response spectrum. I'll take some picture. You can see it here. Okay, this is a concept of response spectrum here. Here I have considered three idealized structures for understanding sake of you. So here I'm considered here three structures. This is the first one, second one and the third one. These are three structures I have considered, and first one is having time period of t1 and stiffness is of k1 and m is the mass. We have represented it as m1. Similarly, in the second structure, it is time period is t2 and stiffness is k2 and mass is m2 here. And in the third structure, the same t3, k3, m3. Okay, and here time period, you already know the how to calculate time period by using mass and stiffness. The formula for time period is t1 is equals to square root of m by k. That is only here t1 is equals to square root of m1 by k1. T is equals to square root of m by k. That's what here I have written it. T1 is equals to square root of m by k. And similarly t2 is equals to m2 by k2. t2 is equal to square root of m2 by k2 and t3 is equals to square root of m3 by k3. These are the three idealized structure. What it indicates, let us know. See here, if t1 is equals to t2, t2 is equals to t3, means if all time period of the structures are same, then for a given component of earthquake ground motion, a maximum response is same for all oscillators. See, can you understand this? See here, if time period is same in all the structures, the maximum response will be same in all the oscillators. Okay, so next here, maximum response of a linear single degree of freedom system to any given component of a earthquake motion depends on the natural frequency and damping. Natural frequency and the damping. Here damping you can consider it is of 2 to 5%. damping can be considered in the 2 to 5%. This is your concept of response spectrum. Okay, this concept of response spectrum says that if we know the natural period of a building, what will be the maximum response of that building to a given component of earthquake can be known from this concept. If we know the natural period of the building, what will be the maximum response of that building to a given component of earthquake can be known from this particular concept. This is concept of response spectrum. Now this concept is extremely useful for in earthquake engineering. This concept is extremely useful for earthquake engineering research and in applying the seismological knowledge and a strong earthquake to a design of a structure. And it is proposed by Hugo Benef in 1934, and later M.A. Bayot extended its application to earthquake engineering in 1941. You people have studied now definition of response spectrum and concept of response spectrum. Now we are going to study how the response spectrum can be constructed. We are going to see now the construction of response spectrum. I'm going to take you into some picture. You can see it here. Okay, in construction of response spectrum, you know already what is response spectrum. Response spectrum is a plot of maximum response of a linear single degree of freedom system as a function of natural period for a given damping. Here the spectral parameters we are going to consider are, namely, first one is the displacement, velocity and acceleration. You can indicate it as SD or capital D, and SV or capital V. Acceleration, S subscript A or capital A. You can indicate it like this. That is these displacement, velocity and acceleration can be related as S subscript D, that is pseudo velocity pseudo displacement is equals to U naught. U naught is a displacement, and SV that is equals to omega into SD. Here omega into displacement. In case of displacement, just they have substituted it as SD, that is equals to, you already know the value of omega is 2 pi by Tn, that is into SD. Okay, similarly for acceleration, S subscript A, that is equals to omega square into SD, that is equals to 2 pi by Tn square into SD. Okay, here as the three spectral quantities are related to the three individual response spectra, are simply the different ways of representing a same information on a structural response. For any infinite rigid structure, that is natural period is Tn is equals to 0. At that time, the mass does not experience any motion related to the base. Means natural period of the structure is 0. Natural period of the structure is 0 means the mass does not experience any motion related to the base, and therefore acceleration response of the mass will be same as the acceleration of the ground, and therefore the acceleration response of the mass will be same as acceleration response of the ground. The response acceleration at Tn is equals to 0, so 0, therefore it is termed as PGA, that is peak ground acceleration. Here in this figure you can see the bottommost figure or a bottommost chart that shows the plot response spectrum. This is the plot response spectrum, that is 12D. The figure number is 12D. You can see the bottommost figure it is, that is the total response spectrum for a given three response histories. The first one and A, B, C are the response histories. As you know, response spectrum is the summarization of response histories. I have told you earlier, the response spectrum is the summarization of response histories. Here A, B, C are the response histories. And here damping is considered as damping, they have indicated it as xi, that is equals to 5%. 5% means damping in all the response histories, it is, they have kept it as same, damping is remains same here, but natural periods of a single degree of freedom systems are different. Hence these systems respond differently to the same strong motion of a ground. The maximum response of several systems such as these, along with their respective natural periods, are plotted to form the response spectrum. Here in this figure, response spectrum is plotted for a figure A, figure B and figure C. These three are combined in figure D. That figure D indicates your response spectrum, and figure C, figure B and whereas figure A indicating your response histories. And here figure A is of time period is of 0.5 and figure B is time period is of 1 second, and figure C is of time period 1.5 second. Here time period increases means the height of the building is also increasing. Here you can see in the picture. If you want, I can send you this particular figure to your the group. Okay, in general the response spectrum is a plot of time period versus acceleration. Time period will be in x-axis and acceleration will be in y-axis. It may be acceleration, velocity or displacement. And here they have considered three single degree of freedom systems which is having a damping of 5% and time period is of 0.5, 1 and 1.5 seconds. 1.5 second means time period 1.5 second means the height of that particular structure is more. Here you can see in the figure, and the figure B is time period is 1, that is it is of some shorter, and in the figure A, that is Tn is equals to 0.5 seconds, that is it is again shorter than these two. Okay, this is regarding your response spectrum, plotting of response spectrum. Okay, now we are coming to design response spectrum. The response spectrum for actual ground motions is quite irregular, and hence the individual spectrum is not convenient for the use in the design. The individual spectrum can be used for a analysis to assess response to a particular earthquake. Now this designed response spectrum is not intended to match any of the response spectrum of any particular ground motion, but it represents the average response spectra of several ground motions. That is known as designed response spectrum. Okay, this designed response spectrum is generally represented in normalized form, as is the case of normalized elastic response spectrum. And it is also shown in IS 1893 2002 and IS 1893 2016 nowadays, and it uses the normalized PGA, that is peak ground acceleration. That is peak ground acceleration in terms of acceleration due to gravity, that is G as SA by G. That is it is independent of peak ground acceleration, and also can be used for different values of maximum expected acceleration for the site. This is regarding your design response spectrum. In this design response spectrum, here in the figure you can see they have shown you natural periods in x-axis in seconds, and in y-axis response acceleration coefficients, that is SA by G. And design response spectrum is of natural period in Tn in seconds, that is and in y-axis they have given you response acceleration coefficient, that is SA by G. And in this figure they have shown you the three types of soils, that is type 1 and type 2 and type 3. The type 1 soil is of rock soil or a hard soil, you can say, and type 2 soil is of medium soil, and type 3 is of soft soil. And here they have indicated in the number of 1, 2, 3, and that solid line indicates the it is of hard soil, and that bigger dots they have, it is indicates the medium soil, and the smaller dotted line indicates it is a softer soil. This is regarding your design response spectrum. Okay, well, today we have completed the response spectrum, the definition of response spectrum, and the concept behind the response spectrum, and the construction of response spectrum, and design response spectrum. These things we have completed in this particular class. Okay, thank you for watching, and see you in the next class. Okay, thank you.